Hey everybody, I hope that your first couple days this week have gone great, and welcome to the back half of the week. I don't know what day you in particular are going to do this lesson, so I know it could be Wednesday, Thursday, Friday, or even Saturday, Sunday, Monday for some of you. I know how you operate. I just was looking to see how many of you finished the homework just since about noon today, and it looks like a lot of you have been on today, so good job there. I haven't graded it yet, but I will in the morning. For today's lesson, we're going to look a little bit more at these graphs that you created last time. So for example, I have the sine function up right now for you to see. There are a couple characteristics that I want to point out to you, some things that we haven't necessarily worked with before. So the first thing, let's actually change the color since I don't have two reds. Let's go with that blue. Perfect. Okay, so the first thing that I want you to look at is our height of our function. Now, we are going to be talking about transformations of functions, so just as a preview, this whole a times your function, parentheses, blah, 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 plus, usually there'd be a k there, but there's a d there. I put that on purpose today. And we're going to look and see what happens when we put letters in these places. But I want to start just with the basic sine of x graph. And the first thing to see is it tops out when y equals 1, and the lowest it will go is y equals negative 1. That a value, when you put an a in front of your sine function, is still going to be your vertical stretch, but we're going to give it a new name today. Stretch. What we're going to start calling it today and for the rest of eternity is it is called the amplitude. You might have heard this word before, especially if you've taken physics. I know my class hasn't gotten to it yet, but Hendrix's class, I know, did wave motion. And sines, as you can see, create perfect waves. So our amplitude here, the most important thing is it is not the height between my two blue lines. Your amplitude is going to be the height from the center of your graph to either the top or the bottom. But even though we gave it a new name, it's going to behave the exact same way a has always behaved. If I'm going to pull up my function, I'm going to set b equal to 1, c equal to 0, and d equal to 0 here, so I don't have any horizontal or vertical shifts. And then if I play with the a value, you guys know when you stretch it, it makes it taller. In fact, if I stretch it so a equals 2, now you can see that the amplitude goes from 2 to 0 when you're talking about the amplitude of what's in the middle. And I can keep stretching it. And then also, just like with other functions we've done before, if you make a negative, it will flip your function upside down from where it was before. I hope that you do take some time with Desmos to play with this. I am going to be doing a couple days of just graphing, so you will have opportunities to play with these things. Alright, so the other thing that I want you to notice that we've not really spent time with before is this idea of repeated motion. We've not really had functions that repeated themselves before, and we've definitely never had functions that repeated themselves for eternity. And by repeating, I mean that I could draw the function in somewhere. And then, let's try that. I could move either what I drew or I could move the graph itself, and I see the exact same pattern repeat over and over and over again. So this is called a period. Period is a new word that we only really use with trig and with female menstruation, and with things that repeat themselves on regular intervals. So one period is just how far can you go before you start repeating your pattern. As I can see here, I'm going to shift my graph because I think it's always helpful to start your period at the point 0, 0. What I can see here is the period is 2 pi long. For the sine function, when y equals sine of theta, or you know what I'm going to do? I'm going to use x. Because I like to use theta when I use angles, but realistically, sometimes it makes more sense for your input to be an x. It means the exact same thing, so don't worry about that. But on y equals sine of x, its normal period is 2 pi. That's something that is worth writing in your notes. I'm not going to stress that bit in great detail today, but my lesson that I upload on Friday is really going to examine what happens when I change the period of my graph. Alright, so just like with my sines, let's go ahead and clear all that out. I'm going to see a lot of the same ideas occur with my cosines. By the way, again, what I'm putting on the screen right now, I do recommend that you write into your notes. This right here is going to be the biggest item, probably, that I'm going to put on your midterm of your new material. So what I'm putting now, I do expect that you're going to remember it past Monday. Alright, so let's go ahead and change the color again, since now I've got a blue graph. I see here that once again, for y equals cosine of x, I have an amplitude of 1. I can see that once again, yeah, let's go ahead and do that from the same place. I'm going to shift this over a little bit. I can see that if I start at the top, here I can go all the way down and all the way to the top before I start repeating myself. And really, you can pick any point you want, just so long as you stop your line before you start repeating the motion you had before. So this right here, I can see again goes from 0 to 2 pi. So again, I have a period equal to 2 pi. So I think this is worth making a note of. For y equals cosine of x, you have a normal period of 2 pi. Again, I'm going to make a big deal out of that on Friday. We're not going to have necessarily normal periods. We're going to talk about what happens when you, let's get it, there we go, when you squeeze this in like an accordion or stretch it out. And we're going to teach you how the math behind that, the number part of it. Not going to worry about that right now, but I do want you to make a big deal out of this whole idea of normal period, because understanding what the normal period is helps you to understand how to adjust your graph in new and different ways so it can stretch like an accordion. Alright, so one more to go. That's the tangent function. On this function, this one always kind of reminded me like a really smooth cubic function. Cubic functions would have a little bit more of a wiggle to them. This one's a little more smooth, and this one repeats itself over and over and over again. And I wanted to show you, I'm going to change my toolbar. I'm going to go ahead and extend my y's out a little bit more. But I'm going to leave the x's about where they're at now. So I hope that you can see, even though they don't draw these in, I do hope that you can see that we have a whole series of asymptotes here. I can see that there's one right here, and here, I keep kind of going over the graph, sorry about that. And here. And again, and again, and again. Technically, I have an infinite number of asymptotes. So, what I see as I look at this graph is, first of all, the idea of amplitude doesn't really have the same meaning. Because this graph stretches up forever, last time with my amplitude, that vertical stretch corresponded exactly to how tall my function was. But on this function, this is already infinitely tall. So when you're talking about amplitude for a tangent graph, one of the most important things is that idea of amplitude actually defines what's happening with this point right here. It's going to define how tall that is and if it gets flipped upside down. And of course, as it moves, the rest of the graph will move. So in this case, when I have, well, actually, don't even worry about that part. When I have my amplitude, it'll get taller. I'm not going to play with amplitude on tangent quite as much. The part that I really want to focus on, though, is, do you see that if I draw in a function and find how often that function repeats itself, it does not repeat itself every 2 pi. I can see here that it is repeating itself only from negative pi over 2 to pi over 2. Or in other words, this one has a normal period of pi. I'm going to make a big deal out of that on Friday when I really delve in deep with this whole idea of how the periods work, and how you can shift them by stretching them horizontally. Again, something we've never had to do before. But right now, I just want you to write in your notes that y equals tangent of x has a normal period of pi. I'm just going to show that part to you now, let you get accustomed to it, and then we'll play with it more later. Alright, so what I want to focus on right now is this whole idea of, I just want to show you how the pieces work. I'm going to go back to the sine function right now. Let's do the one with the transformation in it. Yeah, let's do this one. Let's go ahead, and I'm going to change my y's back because I don't need to go that far. I'm going to say like negative 1.2 and 1.2 just so I have a better, or 1.52, that works too. I have a better view of what's happening with the graph. I can play with my sliders, and I encourage you to do this just to get used to what each thing does. So I showed you that my a value still stretches vertically and can flip upside down. My b value is the new thing, that it can stretch me horizontally. Technically, I could have worked in a b value into functions we've done before, but with your quadratics, your cubics, all of those functions we've studied, putting in this horizontal shift actually just gets absorbed into the vertical shift. It's only when you do trig functions that they do mean completely different things and they have different jobs. Just like before, when you're adding or subtracting something outside of the x, it's going to be your horizontal shift. It's going to move you left and right. And just like before, when you have something on the outside here, where we normally would have the k, that's going to just move you up and down. So, I want you to write out some notes with me. We have y equals, I'm going to go ahead and use the sine function, but really it's going to work for cosine and tangent as well. and 3 other trig functions that I don't think you've been introduced to yet. So, A is called the amplitude now. It's also something we've referred to as a vertical stretch. And we know that if A is bigger than 1, the graph gets taller. If A is going to be between 0 and 1, I should say the absolute value of A, to be proper in my mathematics. Don't worry about it. It just means that we're taking into account when we flip you upside down, we still could be taller than 1. Alright, but if your value is between 0 and 1, your graph is shorter. And if A is negative, this right here is how you're going to see it written out. A is negative in all of your college classes. I don't think I've ever seen a college textbook that writes out the words A is negative. They always say A less than 0 because the values of A that are less than 0 have to, by definition, be negative. Anyway, if you see that, if your A is negative, it will flip the graph upside down. Alright, your B value is called the horizontal stretch. I'm going to get into more detail on that on Friday. Your C value, I should say here, with your B and your C value, they give the horizontal stretch. And C right here gives you the horizontal shift. But they don't equal, so I don't like where I put an equal sign here. I'm going to get rid of that, because that's what we're going to spend Friday talking about, is unlike the other functions we've used before, they do not equal those values. They do not equal exactly what's happening to the graph. But through some simple processes, you can find them if you know your A and your B. Alright, so just one more to go, and it's a pretty basic one. And that is your D is your vertical shift. In other words, it is whatever you see in the D place, it is what moves you up and down. It is the K value that we've dealt with before. I did switch to A, B, C, and D mostly because this C value is not the H value that we used before. We are going to have to treat it differently. So, for the most part, everything here does work the way we're used to, but when it's inside the parentheses, it's going to work a little different. Something that helps me to remember what does what, and I think that you guys have this down, but I'm still going to show you, is the stuff that's outside of the function. It affects what happens vertically. Vertical stretch or vertical shift. What happens inside the function, that deals with the horizontal. And what's convenient about this is that's true of all functions, not just these trig functions. If you think about our function, I'm going to put it down here in the corner, y equals a x minus h squared plus k. The stuff that was outside affected what happened vertically, and the stuff that was inside affected what happened horizontally. Not that different from what we've done before, but I'm just adding one more layer for you. Please, please, please reach out to me if any of this does not make sense to you. I sit on the conference. If you go to your Canvas page and look over to the left where it says modules, quizzes, etc., I sit on the conference page every day from 11 to 1, just waiting to FaceTime with anybody who would like my help. Alright, so what I want to do now is I want to focus on graphing with my trig functions, but I'm not going to worry about any of the horizontal stuff yet, just because I don't want to overwhelm you and do too much in a day. So, we're going to try graphing some functions, and then see how we do. And I'm just going to make these up. I am going to expand this out just a little bit, because I'm probably going to use some horizontal stretches and shifts. But, do I like that? I think I do. Okay, so let's say that I wanted to graph, oh, forgot that. Let's say I wanted to graph y equals -2 sine of x. Now, last time, and I don't expect that you have this memorized yet, but I do want to demonstrate for you. You should be working your way towards memorizing this. The sine function, sine of 0, was 0. The y value on your unit circle at the angle 0 radians, that y value was 0 because you were right on the x-axis. So I had a function originally, and let's maybe color code this. Let's do a purple this time. So if I want to graph just your original y equals sine of x, I know I could graph it just by hitting the button over to the left, but I'm not going to. If I look at what happened with the unit circle, excuse me, then I went through the point 0, 0. Pi over 2 was the same thing as 90 degrees, and at 90 degrees you were straight up. It was like 12 o'clock noon, where the 12 o'clock is on the clock. That's where the pi over 2 was. Pi was back on the x-axis. It had a height of 0. And I have this pattern that emerges. And you, please, please, please check me against what your graphs say. If you don't believe me, here, I'll turn it on so you can see me. Look at how great I did. I'm amazing. So the reason I'm doing this without the graph, though, is I think one of the best ways to get used to graphing is to get used to plotting the x-intercepts. Oh, sorry to those of you who are colorblind. I hope that you can see that. Also, sorry that I put that right on the corner of my screen, so I had to split up the word intercepts. Alright, I think that anytime you're graphing this, you should put in your y-intercepts, you should put in your minimum point, and you should put in your maximum point. And you should be comfortable, not yet, but by the time we finish this section, by midterms definitely, you should be comfortable with graphing those points, at least for your basic functions, without grabbing a calculator. And that goes for sine, cosine, and tangent. I'll do examples with each of them. Alright, so let's see if I can find that purpley thing again. I think it was that one. Okay, so I like to graph one period. This is where I might not get these lines exactly where they need to go, but good enough. And then once I see that period, I know that that pattern is going to repeat itself. I know that I'm going to go backwards 1, up 1, over 1, down 1. And I should see this free-flowing pattern where I very obviously am repeating my motion. Okay, now again, this is the original sine function. This is not the new one that I want to graph. But once I know where my points are on my original function, I can use that to create my new function. I know in this case that my amplitude is -2. I know two things. First of all, I know that that means I'm going to reach a height of 2. My maximum's going to hit the 2, and my minimum's going to hit -2 in height. I also know because it's negative that I'm going to flip my graph upside down. So let me erase some of this extra stuff so we don't make it too busy for you. Oh, I did that one to myself, didn't I? Okay. And let's make that smaller because I've learned my lesson there before. Okay, so if you have an amplitude of -2, but you're flipped upside down, that means that this point right here, instead of being a maximum of 1, now is going to be a minimum of -2. This point that was a minimum of -1 now will be a maximum of 2. And very conveniently, -2 times 0, because the sine of pi was 0, is still 0. So your zeros will stay the same, but your y's, your minimums and maximums, well, that one got kind of swirly there, they will change. And if you want to see how I did, now we can try graphing it. I'm going to bring up my y equals sine of x. I'm going to change it so that my a value is -2. I want my b value to be 1 exactly, because if it's 1, then 1 times x is just x, and just x is what I have. I want my c value to be 0. And I would say mine doesn't look nearly as pretty, but I think I did an okay job graphing where that's at. And that okay job is all I'm asking for right now. So, if you have any questions, again, please, 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 let me know. Let's do a cosine function. Let's do, I think I'm going to add a vertical shift in this time. I'm going to do y equals 1.5 cosine x. Let's see, what would be reasonable? Let's say -2. Yeah, I like that. Alright, so I'm going to turn this off again just to demonstrate to you. What I want you to do is I want you to start thinking about what did the original base function look like. And when I say that, I mean just what did your regular old cosine of x look like. With cosine of x, if you look at the unit circle and you remember that the x values of the coordinates on the unit circle also correspond to what the cosine of that angle equals. When you were at angle 0 radians, you actually had an x value of 1. So in other words, that was your maximum point right from the beginning. When you went up to 90 degrees, or pi over 2, the highest point on the circle, you were right on the y-axis, so therefore your x was 0. Your cosine here will be equal to 0. And you can double check me against your unit circle in the activity we did 2 days ago, but these points should be on your worksheet. Cosine, if I was making a table out of this, by the way, x, y, I used 0, pi over 2, pi, 3 pi over 2, and 2 pi. And if I just plugged in cosine 0, I got 1. Cosine pi over 2, I got 0. Cosine pi, I got -1. Cosine 3 pi over 2 gave me 0. Cosine of 2 pi was back to 1 again. I do expect that you are checking your unit circle on this and using that knowledge together with what we're doing right now. Alright. Once you have one period drawn in on your function, go ahead and finish filling in what would naturally flow. Right now I can see that I have this pattern, and I know that I'm going to keep following the pattern right now. Maximum 0, minimum 0, maximum. Over here I have maximum, and then 0, minimum, 0, maximum. And if you draw it in, you just use Desmos to check yourself. But my goal again is that you don't spend all of your time letting Desmos do all the work, because you're not going to be able to use Desmos necessarily next year. Depends on your teacher, but if it's a college class, they will not let you. Alright, so we have our basic cosine graph. I've got two things going on right now that I need to deal with. It's always a good idea to focus on the multiplication part of it first. So, I know with that 1.5 out in front that is my amplitude. And conveniently with the cosine, that just by definition defines my new minimum and maximum. So, I'm not going to... Actually, yeah, let's go ahead. Because I'm only graphing right now y equals 1.5 cosine of x. I'm not going to worry about the vertical shift yet. One thing that I do recommend when you're graphing one of these functions by hand is that you only try to work with one transformation at a time. If I try to graph something that has both the new amplitude and the new horizontal shift at the same time, it can be overwhelming very quickly. This is where I probably shouldn't have color-coded to blue yet. That's okay. I will change the color of my original function. So at this point I feel committed with the blue here. Alright, so here's the function just with our new... Oops, I put that one in the wrong spot. Our new vertical stretch. Like I said, let's go ahead and recolor code that. Ugly, sorry about that. So now that you have this new blue function, what we need to focus on is moving everything down 2. And so it means literally this point right here, that's 1.5, needs to move down 2 so that it's at negative 0.5. This point right here, that's at 0, needs to move down 2 so that it's at negative 2. And this point, that's our minimum, that's already at negative 1.5. Negative 1.5 minus 2 is negative 3.5. And we're going to see our values shift in a consistent way. Let's go ahead and graph what I've got so far. This moves down to about there. And so on and so forth. Is it more steps? Most definitely. But I gotta tell you, if you think that math is something you should be able to do in your head, or math is something that should only take one line in your notebook, then you're gonna be in for a really rude awakening when you head to college. But if you learn how to do this one step at a time, you're gonna learn it more deeply than most of your peers will. And that's what I'm really focused on. It's trying to get you to learn it more deeply so that you have an advantage over the rest of your classmates in college. Alright, so let's see how I did. I am going to graph the cosine function. My a value this time was 1.5. My b value still, I'm going to leave it at 1. There was no c value. And my d value this time was negative 2. Alright. Hey, I even matched the color that time. That was not on purpose. Again, not perfect, but I think I did a really good job. I'm going to erase all of these previous lines that just me to get to where I needed to be. Can erase those shift lines as well. And when you make the graph a little less messy, it's a lot easier to see how well we did. I do recommend, personally, and this is just my personal preference, it is okay if yours is different. I do recommend that you do show all 2, 3, 4, there won't be more than 4 though, but 2, 3, or 4 graphs all on the same XY coordinate plane. Just so you can show yourself. And I also do recommend, you notice how I color-coded things as I went through? I had a red function, I had a blue function, and I had a purple function. I do recommend that you use colored pencils when you're doing this by hand, so that you can remember which line goes with which thing. Because when you do have this many lines, it does get confusing. But from what I found, graphing it by hand like this, you're going to learn it more deeply than you would just focused on Desmos. All right. Let's do one more. I'm trying to decide. Do I want to play with tangent? What do you guys think? Most of you are saying no. I can already hear it, even though you haven't seen the video yet. I know you're saying no. Let's not play with it yet. Let's do just another cosine function. No, let's do a sine function. Let's do both a stretch and a shift in the sine function. Let's do something like y equals 5 sine x minus 1. Okay, and that's in purple. Let's pick another color, and let's go back to my original function. Y equals sine. Play with your unit circle, get used to this idea. Sine starts at 0, cosine starts at 1. Sine then goes to a maximum 0, minimum 0. If it was cosine, it would be maximum 0, minimum 0, maximum. Just patterns you're going to get used to the more you do this. And by used to, I mean it's going to take you like 50 times before you really get used to it. You're like on time 2 or 3 right now in your experience. Once you have the pattern going, go ahead and finish it off for as far... Usually we like to do 2 periods here. So 2 periods would be going from negative 2 pi to 2 pi. That's actually the most common you're going to see in most of your trig classes. I'm just going to show you whatever I've got on my screen though. All right. So there's my function, but only for my basic sine. Again, you want to take care of, I think it is easier to go ahead usually and take care of the stretch first. Personal preference again. So I now have something that's 5 times as tall. I am going to go off the screen here. I do realize that. That was my own fault, but I do realize that. I'm going to say it goes about there, even though I know it's a little bit beyond that. Just this screenwriting technology, I don't have the freedom to move my dots like I did. Actually, I don't think I do. Let's see. Can I move them? Nope. This isn't the same technology that we use with your smartboard. Okay, that one I put in the wrong spot though. That needs to be over a little further, because it needs to go over the 3 pi over 2 over this maximum. Alright, and my zeros, because I haven't moved it yet, stay the same. 5 times 0 is still 0. And I see something that's just the same function but taller. It got stretched vertically. Now I should type in, this is my function y equals 5 sine of x in the blue function. Now when I move to my purple function, all I need to do is I need to move each point down 1. So I like to personally put these points in. I call them my anchor points. I don't pay any attention to the red function at this point. The blue is the one that I'm shifting. It's going to go down a little too far and then come back up. This one there. You see how neat I am in my graphs? I always kind of laugh when a lot of you say, oh, my graph looks so sloppy, and I just kind of go, listen, kid, I've been doing this longer than you've been alive. Mine still are sloppy. Don't worry about that. Alright, now for the sake of what we're doing, I'm going to go ahead and I'm going to erase everything except for my purple graph, because ultimately the purple graph is what I'm looking for. When you do this on paper for me, and at some point you will be, I'm not going to have you do it for your assignment today, but at some point you will be doing this on paper, you do not have to go through and erase all of these lines that are not your final graph. I just prefer usually that you use colored pencil on the first couple graphs that you use, but then once you're getting to the final graph, I want you to be using, usually a dark pen or pencil, something where you can shade it in pretty thick and I can tell which one I'm looking at for your final answer. Now those are close enough. Try not to erase my full function. Oops, got a little too much on that. This markup software is convenient, but it is not as convenient as your smartboard software that we use in the classroom. By the way, if you want this app, it's a Google add-on called PageMarker. It lets you write on any website. I'm finding it's pretty handy for what we're doing right now. Okay. Only thing is I forget to switch between these sometimes. So I did a sine function. I'm going to turn my sine function on. My a value is 5. My b value is 1. My c value is 0. And my d value was -1. So how'd I do? Nothing gorgeous, certainly, but I think I did an alright job. In fact, I did a better job getting these points on the line itself than on my graph. My graph is off. But the points that I labeled, I don't know if you can really see that. Let's do pink. We haven't done any pink yet. This purple dot I have right here is right on top of that line that Desmos drew, not the one that I drew. So while my graph was sloppy, I definitely had some points where I was exact. And again, I'm talking about the Desmos purple line, not my purple line. So, what I want you to do for your homework today. Do I still have it up? I might have taken it down. I have this for you on... Oh, wait, it's right here. Okay. What I have for you today is I want you just to practice dragging some points to make your graph. And observe what each thing does. You're going to have an amplitude change. You're going to have a vertical shift. And this one is going to have an effect on the period. You don't have to worry about any mathy questions with period until you get to about here. But even then, I just want you to play with making the period. Here, I use this equation. We're making something that has a amplitude of 4, a period of 6, and a vertical shift of 3. And you're making it physically with Desmos here. And then it's going to talk to you about this is what that function would actually look like. or sorry, no, you want to adjust this number so that you do have all of those things. And again, let's mark this up. I'm not going to do your homework for you, but I do want to show you these things. Again, your amplitude is measured always from the middle. This is something that's already been shifted. But if I go from the middle up to the maximum on this, I can see that that is 4 units. So this does have an amplitude here of 4. My period is how long it takes me to repeat my motion. So I go up, I go all the way down to the minimum, and I come up. If I go any further than this point right here, I am going to start repeating my motion. So my period here, I can count out my boxes as 1, 2, 3, 4, 5, 6. And my vertical shift because I'm dealing with a sine function. Oh, yeah. I do that sometimes. So happens when I forget to slide this one over. My sine function, remember, normally starts at the point 0, 0. I'm going to keep saying it just because I hope the more I say it, the more you're going to get comfortable with it. Again, I don't think you need to have it memorized yet, but I am thinking by next week you should. So sine starts at 0, 0. I can see here that this one started at the point -3, 0. So right there, I can tell I did have a vertical shift of -3. So what this problem wants you to do, let's go ahead and clear all that, is it wants you to play with the numbers that are on the outside here until you get a function that matches the blue line. So for example, I'll give you this one. If you put the 4 here, that had an amplitude of 4. Obviously, the vertical shift, you know that exactly. With the period, what I'd like you to do is just play on another screen with Desmos. And I want you to adjust this B value here until you get something that has a period of 6. I'm going to teach you the shortcut next class, but I just want you to play with this right now. This is going to be a completion, so if I see you tried every problem, you will get full credit. Okay, so, and you only have to do that mathy part. Where are we at? That was problem number, oops. Oh, this is the part I want to go away. Thank you for being patient, learning all sorts of new things here. So you're using an equation on problem number 6, page number 7, 8, these last couple of functions. And then you build your own and have fun. And I do want you, by the way, yes, I do want you to trade with a classmate. So in other words, I want you to create one, and then I want you to go and try to solve somebody else's problem. Okay, so if you have any questions, please let me know. I've been getting more emails from you guys today and yesterday than I had before. And I've only talked to a couple of you on the Canvas conferences so far. So really and truly, from 11 a.m. to 1 p.m. every day, I sit at my computer. I keep my webcam turned off until one of you gets in the conference. But once you're in there, we can chat face to face and we can work through any problems that you have. So let me know what you need. You have your attendance points, your quiz, and your assignment up on Canvas. And I will chat with you more on Friday.